Okay. Okay, we're going to talk about musical inductance. It's like a coil inside coil. We talked about that last week. In lab, we take one of these small coils, put it inside the Helmholtz coils, put a current through the Helmholtz coils. When that current varies, the magnetic field varies, so the flux inside the little coil varies. When the flux inside the little coil varies, it induces a voltage, which in the case of a conductive coil, causes a current. Okay, so that's pretty straightforward. If we have the basic principle that the induced voltage is the rate of change of the magnetic flux. Okay, we have to know how that applies, but right now think of a coil inside a coil or a solenoid inside a solenoid, a long coil. The coil we have here, as I talked about before, is not a tightly wound coil. Okay, it spreads out about this far and it's about this big around. It's not exactly a solenoid either because it's not long enough that you can neglect edge effects. So it's something in between. It's an animal itself. And we'll talk a little bit more about that. The Helmholtz coils are pretty tightly wound, two tightly wound coils that both produce reinforcing magnetic fields when you put currents. Okay. So that's basically what that is. Now we'll talk about it a little more in detail. But I just want to kind of tell you what we're going to try to talk about today. Also keep myself on track so I don't go off on a tangent because we're up to short time here. Self-inductance, you have a single coil. Or solenoid. Doesn't have to be a coil or a solenoid, but it's probably going to have characteristics that you would think of in terms of how coily is it, how solenoid is it. At this stage, we pretty much can find our potential coils and solenoids after this course. Yeah, single coil or solenoid. Change in current. Changes the induced. You know that. Use B field, magnetic field. Changes the induced magnetic field inside. As the magnetic flux changes. Inducing the voltage. Resist change in current. Basically, it's what self-inductance is. Calculated. Inductor is a device of self-inductance. L is going to be the inductance. And the induced voltage or induced EMF is negative L times di dt. Why? Well, if your current changes, that changes the flux inside this thing. Just think of a coil or a solenoid. Change the current, change the magnetic field, changes the flux. If you take the geometry of the device into account, you can derive its ideal inductance, which is what you would multiply by the rate of change of the current to get the voltage drop due to self-inductance. Okay, we'll flesh this out, talk more about it. That's what I'm talking about. Magnetic field energy of an inductor is the work with energy, let's say. It's the energy to build the current. Why does it take energy to build the current? Because as you build the current's changing, so the flux is changing. The flux is changing so that there's a back EMF, so that whatever it is you're using to try to charge this thing up is being resisted. And even if there's no resistor in the circuit, you're going to feel some resistance if you're trying to crank the thing. Put it that way, okay? It's going to take energy because you got to overcome this voltage. And the energy it takes to build the current is, okay, well, everything's accelerated. I'm going to use U because it's a potential energy. Okay, once you get this thing charged up, it's got a potential energy. What's that? It's the integral from 0 to I, say I max, it might be hard to read. And that's a very simple integral. It's 1/2 L I max squared. If you want the density of the energy in the thing, you divide by the volume. So if I increase the current here to, let's say, 20 amps, and if I've got a 20 amp current through here, it's going to get pretty hot. We don't want to keep that going for long, okay? Even if there was no resistance involved, we take energy to build that magnetic field. That's how much energy, where L is the inductance, self-inductance of this coil, which is not that difficult to calculate. We'll go through the details, but that's what we get. If we divide this by the volume inside that coil, then we get the magnetic energy density. Okay. got a little more reflective, I'll use it. Now, after this, we just get into the equations. And they're just very simple differential equations that you learned to do last semester. Since you learned to do the differential equations, there's a lot more I can say, but I don't want to say too much because not everybody that watches this video, all my groupies out in Antarctica and places, might not have had a differential equations. But it's very simple to talk about these things. Okay, so LR circuit. In all cases, we're going to assume the net voltage drop to zero. Okay. In an LR circuit, then voltage drop across the inductor is this. And the voltage drop, the voltage change is this, so the voltage drop is just L di dt. Voltage drop across the resistor is IR. That equals zero. And that's just a separable differential equation. It's really easy to solve. Solve that equation about October of the fall first semester calculus class. Okay, if not before. Depends on how fast the class is going. You don't even need the techniques of differential equations. Okay. LC circuit. You have L di dt plus Q over C equals zero. Now this is what happens. Okay, let's just say that we've got an inductor and we've got it charged up and now we've got a current in, okay? And then we attach its leads, take it away from the source, attach its leads to a resistor. We're going to have this, okay? Now this circuit had better be superconducting, otherwise it's going to dissipate its energy to the resistance of the circuit itself. But of course, that's covered by this as well, right? Okay, so there we have it. Okay, so here's your LC circuit. Again, you charge up your inductor, throw a switch to put it in series with a capacitor. And what's going to happen is it's going to discharge, which will charge the capacitor up, which will then discharge and charge the inductor up, which will then discharge and charge the capacitor up, which will then discharge and charge the inductor up. Okay. We'll talk about that. We're going to see that in lab Friday. So one good thing about, switching to lab day until Friday is just that we will have seen all this and we can see it in action and understand what we're seeing. Okay. So anyway, you got this. Okay. Now you've got two variables in here. Capacitor, the charge is varying and the current is varying. But of course, the current is the rate of change of the charge. And that's just a whole lot like mass times acceleration. Okay. And this is like a restoring force, linear restoring force. Just totally analogous, and it's solved exactly the same way. You don't need a differential equations course to solve that. Although you can. You just trial solution Q equals AE to the RT, plug it in, and you get imaginary R, etc. Complex R. And so forth. But you don't need it. You just need a little common sense about what the second derivatives of sines and cosines are. Okay. The LRC circuit is just a list of voltage drops and if the total voltage is zero, there you have it. This is okay. As before, we've got I and we've got Q, and we know that I is just dQ dt. So you have L. I'm not going to write out the ddt notation. I'm just going to say LQ prime plus LQ double prime plus RQ prime plus Q over C equals 0. And this time, you really do want to plug in Q equals AE to the RT and just do what you do with second order linear differential equation. Okay. And that should be very familiar. And if it's not, it'll come back to you when you see it, because you did it for the spring mass dash pot system, and it's exactly the same equation with different letters. This circuit behaves exactly like that spring mass dash pot. We don't have dash pots. We have springs and masses. We look at some of the stuff that they do, and they're, well, detail. But there it is. Now, unfortunately, we don't get to complete a study of AC circuits because a lot of times you want to drive these circuits with some voltage. Okay, matter of fact, almost all the time you want to do that, okay? Which means you're going to have some voltage function here on the right-hand side. What do you do with that voltage function? Well, this is a simple linear equation. You can use an integrating factor and solve it, or you can just use trial solutions. Okay, method of undetermined coefficients. You usually don't have to go to variation of parameters, but you could if you needed to. It'd be a pretty weird circuit. I'm sure you're going to encounter. You're going to be an electrical engineer. You're going to encounter that. Where they make you actually solve the thing or just give you some software formula or whatever. I don't know. Hopefully they make you solve it. I think it makes better engineers if they know what they're doing rather than just plugging it into a black box. Still, you've also got to teach engineers to get things right so they build things and they don't blow up with people. So they get to balance that, and I'm glad it's not me balancing it. There'd be all kinds of disasters in the world, but it'd be theoretically beautiful. Okay. If I designed it, somebody else would have to implement it to make it really beautiful. I make too many mistakes. Okay. That makes sense. That's it. That's it. That's it. And then you go into AC and you just make that right hand not zero and interpret what you got. You've got all the techniques of differential equations apply to that. Okay. So it shouldn't be a difficult transition for you because of the weird start to the semester. There's just no way I could push you hard enough to do that last chapter. Okay. I mean, yeah, I could have. Would have been good. Okay. Still quite a bit. So let's go through some more of the details here. Let's see how it works out. And in lab, we'll actually get our hands on the stuff. Okay, let's just say we've got a coil. Got N one loops. Fair enough. We'll call this coil 1, but then one. Coil 2 in the same plane. On the coil 2 and 2 loops. Radius R2. So I might talk about R vectors, but it's use A2. Now, and you both likes to use lowercase I a lot of times. Current. I don't like to because you get into the square root of -1 I a lot. So I kind of like the looks of the lowercase I. But just say this. Okay. And I've got my ones and twos. If we assume the field within is equal to the field at the center, what's the flux due to the current I2? And I'll say I2 of T, just to remind you, we assume it's a time varying current, or that it can be a time varying current. Time isn't varying, there's no field, because there's no change in flux. I'm sorry. I take it back. There is, yeah, there's no change in flux, it's not induced. EML, but there's certainly a magnetic field, even if I2 is constant. So what's the current I2? Remember? It's formula. Well, don't necessarily expect you to have that formula. You know, derive it. Remember, you say, okay, L integration. Over here, so look here. There's a loop. You got a current I. You got the center. You got a delta L here. And here's field at the center, which are R vector. R vector perpendicular to tangent. Remember this? Okay. So that the field at the center the sum of your I delta L cross R we got our half divided by A squared all times K prime. Well, the total by delta L is 2 pi A. Cross product is just going to give you the I delta L as its magnitude. It's 2 pi I times K prime over a squared, which is 2 pi, and I left off pi, 2 pi I over a, and it's times a prime, which your book tend to write as um, I over 2 mu naught A, since mu naught and K prime have that 4 pi relationship. And I think that's the formula your book has, but this is how you get it. You need to know this. Something I could certainly has a relatively high priority of appearing on the exam. Explain that. It's a pretty standard thing, including even on the axis. So anyhow, we have that. So what's the flux? Better figure out what the flux is. We did this kind of fast. And I put my view in the wrong spot. That was used with reciprocal relationship for the permittivity of the electric fields. That's right. It should be mu naught. In general, if you have the substance that increases the permittivity of space, then you're going to use mu and you multiply that by the coefficient. That's straightforward. Okay, so what's the flux? Got the flux? Well, I'm going to tell you what the flux is. I'm going to take time today to get over your shoulder and check that. The flux due to I2 then is what? We assume the field on, hang on. Okay. U naught I over 2A. Remember, I is a function of T, so we're going to keep reminding ourselves of magnitude. Assume this field inside the coil. Area is your number of loops times IA squared. IA2 squared. Phi B, that equals M1 times pi A2 squared times your field. So you're going to have A2 which you raised to 2 squared feet. You got that. Then you got a factor of 2 in your denominator. And you've got an M1 pi mu naught I of T. I'll put the I of T out there last. Now, if I did that right, and I'm not going to double check, that's how you get it. That's the magnetic flux. Well, then the induced field from loop 2 is, and let's put a 2 on it. No, that is a formula set in stone. There you have it. Induced, I say induced field, and I've been doing that. Induced EMF. As a result of the field and so forth. Okay. There's our induced EMF. We have exactly the same flux change due to this current in the bigger coil. So you get the same EMF in the bigger coil. If you don't have any current in the big coil, what's the ever? Hang on. It should be I2T. It should be I2. Be I2 throughout. There we go. Well, this equals L d I2 dt. And there's another sign out. Yes. All right, that's pretty straightforward. If we understand the induced EMF is rate of change of flux. It's not accurate if you actually take it into the lab and measure it. It's going to be lower than that because the field is not uniform inside the coil. The field is greater at the center. Doesn't fall off all that much until you get out really near the edge. Okay. Till you get out really close to the coil. So it's a pretty good approximation. I forget how close the approximation would be. I think there's a percent. I'm just speculating. I expect there's some percent for coil, for tightly wound coil, that you apply to this. I don't think it necessarily depends on the dimensions of the coil. But I'll be glad to be clearer on that. Okay, so that's just one example of a mutual inductance. Now, if you had a current through the bigger loop and it was changing, it created a magnetic field that changes the flux in the smaller loop. So you should look at the formulas and so forth and see how they come about. The formulas are easy to use. So, we learned to do transformers in high school. Most of the class we do, because just simple proportionality. Okay, that's mutual inductance, and actually I kind of confused two things. This would be the self-inductance of loop 2. But of course, the flux through loop 2 is also through the big loop, and let's deal with that. If we had a solenoid, we'd use Ampere's law and stuff to get the magnetic field. And again, figure out what the magnetic field is as a function of the current and take its derivative. And we would then very quickly get the inductance. And I'm pretty sure your text does that in some of the examples. Okay. Yeah, we're gonna try to measure some of that. Now, inductance is kind of hard to measure because we don't have huge inductors. And there are units around inductors. You ought to read about it. It's called the Henry, and it's what you multiply by the rate of change of the current to get an EMF. So it's just got units of EMF divided by units of rate of change of current. Okay. Amps per second, EMF in volts. Okay. Volts per second. And that's a unit of L, and that's called the Henry. And I think we got 10 millihenries in an inductance box that pretty much worked on most settings last year. I haven't checked it out for this year. So hopefully we'll be able to do some of that. We'll also attempt to measure the self-inductance of this little coil with an iron core. Got to remember, I wish I knew where those bolts are. And I took some good 8-inch, 5/8-inch bolts. They were temporarily helping to brace my deck. I haven't taken them out, but I just got to drive them out. And when I do that, hopefully I'll remember to put one in the beading and have one here. So we can do that. Or we can use the smaller bolts, which work pretty well. And just see if we can measure the results of this, which is just an exponential change in the current. Okay. It happens over a very short time because we have a pretty small inductance. And we'll look at the equation in a few minutes and see what we are going to expect to see. Okay. Any questions? Does that halfway make sense? No. This is it for the magnetic field energy. Okay. And let me back up 1 second. Okay, actually, this wasn't right because I didn't include I in here. So let's talk again about where the center comes from. Okay. L di dt is your EMF. Okay. And if you multiply your voltage times your resistance, you get energy. So you're integrating Li di, and the integral is just as I said. The integral of L di was not this. I just happened not to write down the I, and I didn't really explain. So again, just multiply your voltage. And why does that work? It's your voltage, it's your number of joules per coulomb. Okay. By your current, which is number of coulombs per second, you get your number of joules per second, which is your power. Then you integrate that power and you get your energy. Okay. It's a very easy integral. You're just integrating essentially x with respect to x, which is x squared over 2. Limits of 0, whatever. And there it is. And that brings us to these equations, which you ought to be real well equipped to understand. So let's move on to that. Let me get some board space. Okay, here's the equation for an LR circuit with no voltage source. This can be rearranged to the form di dt equals negative R over L. And in this form, um, what's going to make sense, what's going to have a good solution. Then you write the equation down correctly. Okay, now this will work again. Di dt equals negative R over L times I, which means, of course, that di over I equals negative R over L dt. We integrate both sides. We get natural log of the absolute value of I equals R over L t, which means that I equals A e to the negative R over L t. Calculus is rusty, so rusty you don't recognize that. Review it. Fundamental. Comes up again and again. You're going to see it again. Especially, yeah, you're going to see it here again too. Okay. Um, Now we say the absolute value of I. So I suppose we ought to say the absolute value of I equals AE to the whatever. So that I could be plus or minus A E negative R over L D. Or we could just say that A is any real number, which means A could be positive or negative. So then we don't have to put the positive or negative in. All right. Well, there it is. This from elementary pre-calculus, we see that this is decreasing exponential function. We see that its time constant is the time it takes all to 1 over e. In other words, the time it takes for this exponent to become -1, which is L over R. The reason we're going to have some trouble observing this, we've managed a couple of times in class to get a signal that we think is observing this, okay? It's not easy. So we're going to have fun trying to set that up. Reason this can be challenging is for these coils that we have, L is really small. And R is the resistance of the coil, which isn't that small. So the time constant is really small, which means that the thing happens in tens or hundreds of thousands of a second. Well, that's going to be kind of fun and interesting. Hopefully, the resistance box will work. We'll be able to get something we can actually observe and get a good curve. Okay. And the half-life is the time it takes this to fall to half, and it's going to be about 0.7 of this. Okay. So it's going to fall to half, about 17 of its time. Okay. And that disposes of this. This is simple. You can do this halfway through a first semester calculus course. Of course, you don't want to develop the whole concept of AC circuits, okay? In a first year calculus class, you just solve the differential equation and without a lot of interpretation many times. Okay, so there it is. Okay, the LC circuit is a little more interesting. Now we can write that as L Q double prime plus Q over C equals 0. So we have Q double prime equals negative Q over LC. What function Q has a second derivative that's a negative multiple of itself? Well, it's one of the first things I ask you early in the year. Okay. It was MX double prime equals negative KS. Get X double prime equals negative K over M X. So X equals some multiple, the cosine of square root of K over M T. Or some multiple of the sine of the same thing, or some combination of those, which gives you make this a B, make this a C, and X will equal A cosine of omega T plus phi. Just use a little trigonometry, that whole development that we did back in September. You're going to get a very similar solution here. I'll work it through in a little more detail. Just reminding you something I hope you retain at least some residual awareness from several months ago. Okay. How do you solve this equation? Well, one is just by inspection. Pretty much what I just said down here. How do you conclude that? What function has a second derivative that's a negative multiple of itself? A sine or cosine. Y'all gave me that answer back in September after you thought about it a couple of minutes. You want to retain that idea. It's really important stuff in mechanics and electromagnetism. Okay. So you can just check it. You take a stab with this and then you say, okay, let's see if that works. What's the second derivative of the cosine of 1 over square root of 1 over LC? Well, chain rule tells you the first derivative, you're going to have a negative sign of this multiplied out front by square root of 1 over LC. And the second derivative will then be the negative of the cosine of this thing with another 1 over square root of LC. And those 1 over square root of LC's multiply out to give you 1 over LC. So you're going to get 1 over LC times Q. Now work out the details of that if you need to. And I'm not going to go to the, I mean, you can, again, if you use a trial solution, like an E to the RT, it's going to come out here too. But I'm going to do that on this equation, so I'm not going to bother with it. And then when I do it on this equation, like, well, what if R is 0? Well, then you get the solution to this. is the solution of this equation, the solution of this. Okay. And as far as that goes, if C is equal to 0, you can also get the solution of this first. So let's look at this equation just to refresh you on something you haven't done for a few months. Presumably haven't done next time. Okay. We've got L Q double prime plus R Q prime plus Q over C equals 0. Again, these are the voltage drops around an LRC circuit. So you've got an inductor here. You've got a resistor here. Let's say you've got a capacitor up here. And somehow you've got a current in this thing. So one way to get a current in the thing is something you understand. You charge up capacitor, discharge up the capacitor, then takes the clips off. The capacitor is going to discharge, which tends to increase the current in the inductor, limited by the current, by the resistance, and maybe this is resistance of the inductor. Okay? So you could only go so fast because of this, and even slower because you're increasing the flux within the inductor, which fights the increase of the current. All right. That's what's going on. And this equation tells you how that all works out. Okay, so that don't really need the A out right there, but in general, you do have a constant multiplier that just goes along for the rise. Use the form of the equation. So we have Q double prime all by itself, then we have R over L Q prime, and then Q over L C. Let's say that we get our R over L that we have. Do something so we'll back here. Okay, it's going to be part of our solution. You've got the Q over L C thing. That reciprocal L C is going to be part of our picture. Okay, so what do we get? Well, double prime is going to be, and I'm just going to factor the A out. And you're going to have a factor A in every one of these. I'm just factoring it out because A is a constant. The derivatives aren't going to affect it. We're going to get R squared. I'm even going to do this. It's A e to the RT, because every derivative of e to the RT contains an e to the RT. Really, all we're interested in is a characteristic equation that should be familiar to you, right? Characteristic equation just pops out. So we have R squared for this plus big R over L times R plus one over LC equals 0. So what is R equal? By the quadratic formula, it's negative R over L plus or minus the square root of R over L quantity squared minus 4 over LC all divided by 2. Anything there that's not pretty obvious? Really, most stops and red equations at this point. And to see if I did something wrong too, might have. Okay, now we've got a lot of flexibility in how we format this solution. This is just fine. We can plug it back in here. And we're good. We've got a couple of questions, of course. It's just quantity here positive or negative? Is this discriminant positive or negative? If the discriminant's negative, we've got a complex valued solution, right? Okay. So we're going to have like a negative R over 2L, real part, plus some imaginary. So it's going to be that imaginary times IT and all that stuff. Okay. So what's the nature of the solution? Before I get to the nature of the solution, I could write, I could just write the question. Real? Is it complex? Okay, put it in the form. If we factor R over L out of here, then the R over L squared is going to become 1. And then we're going to, it's like we're dividing by, or multiplying by L over R squared in there. If we multiply by L over R squared, we get negative, well, we get 1 minus or over RC, all that over 2. Now let's just be careful. If I multiply through by R over L squared, then I'm going to have something wrong. I'm being careless with my algebra, so I'm going to have to write it out a little more carefully. Okay, so let's just see. R over L squared minus 4 over LC equals R over L times 1. And of course, factoring that out, then it's R squared over L squared times 1. Factoring that out is like multiplying this by L squared over R squared. I multiply this by L squared over R squared, I get not negative 4 L over R squared C. And then when I do the square root, squared R squared over L squared becomes R over L. This becomes minus 4L over R squared C, which doesn't look right to me either. Well, the units kind of badly written here. You can write this as negative R over L, R over 2L times 1 plus or minus the square root of 1 minus 4L over RC, over R squared. Are the units of L over R squared C, do the units cancel out? Because everything else is unitless. We have units of R over L here. Well, maybe not. Maybe I've got the arithmetic wrong. Not too important right now because we're not going to actually try to apply it. And that's no excuse. I don't do that arithmetic. I don't want to get off into the units of these things right now. You pretty much go back to fundamental units. It gets a little messy. The point is now that if this quantity is greater than 1, you have a complex solution. Now, what makes this quantity greater than 1? And that's the question. Okay, what you have to know, what has to happen to L, R, and C to make this greater than 1? Okay, now, not take it too clear. This is another possible form. Turns out the form we want. And we don't really have a lot of time. I've had you work it out. We want to factor out the square root of LC here. Okay. Now, if we factor out the square root of LC, then we got to multiply this by LC. And, you know, and you're going to get R squared times LC minus 4, and that doesn't even seem reasonable. Maybe I ought to go back and learn how to do algebra. Okay, hang on. Okay, this is nothing but algebra 2. Let me just say somehow things aren't coming out the way I want them to at this point. If you look at this, any of these expressions, now what I'm going to say doesn't make any sense. Hang on. Okay, just take all those rearrangements, put them aside for the moment. This is complex if thing under the radical is negative. Okay, so what's the condition? The condition is that four over LC is greater than R squared over L squared. And we could multiply both sides by L. And I still don't like that. Is there something wrong with what I wrote up here? I swear this is straightforward, plug into the quadratic formula. And I don't see any problem between here and here. We divide all this by L. Those are the coefficients we get. And it's not leading to what it needs to lead to. Okay, bottom line, if this is negative, we get an oscillatory solution because we're going to get like a e to the IT, right? That's going to give us a cosine of IT plus a sine of IT type thing. Is that familiar? Should be. Okay. If this is 0, then we get an exponential solution. Just R equals negative R over 2L. It's just e to the negative R over 2L times T. And that's just an exponentially decreasing solution. If what we have under here is positive, we get two possible solutions, which behave a lot like the exponentially decreasing solution, except they take longer. Okay, so it comes down to that. It comes out very easily from these symbols that somehow aren't working out. Okay, we'll work out the symbols next time. Make sure you understand all this in terms of your, I mean, as best you can. I'm not going to test you over your differential equations. I'm not going to ask you to derive the solutions, but I will ask you to interpret these solutions. And this corresponds to overdamped, underdamped, and critically damped systems. Critically damped is when this thing is zero. Overdamped is when this discriminant is positive. Okay. And underdamped is when you have the oscillatory solution. Read the text. And we'll pick up the rest of it next time. Okay, I stretched around a little bit. Let's just quickly. It's an addendum, but it's part of the thing. This equation is the same as this equation if R is zero. Okay, so by inserting R, things happen. If you insert just a little bit of R, remember this gives you an oscillatory solution for reasons that ought to be very obvious if you just think about them. The sines and cosines come out naturally, in a very straightforward way. That mimics what we did early in the first semester course with harmonic motion. Okay. So by inserting an R in here, you now start damping out these oscillations. Okay. And the greater they are, the more they damp out. If R gets big enough, they damp out so much that they don't oscillate. Okay, so your oscillations, the board space, hang on a minute. Simple harmonic motion. Undamped LC circuit. Have this. And phase shifts and all that happen in the way we see, just by combining the various strengths of the sine and cosine contributions. But the simple harmonic motion, the undamped LC circuit or the undamped LC circuit act like this. Now, damp the simple harmonic motion or add resistor to LC. For small resistance, what's going to happen is you're going to gradually damp out your oscillation. I'm not using gradual out here, but your oscillations theoretically continue forever because the exponential decrease never ends, never reaches zero. Now, eventually you get down to where you have a negligible probability of that last little quantum oscillation. And we don't worry about that, but the thing, in fact, does have a high probability to hit zero. And even before that, the noise, the quantum noise, is going to overwhelm any oscillation counters. So effectively, it does hit zero at some point. Okay, so anyhow, damp simple harmonic motion or add some small resistance. Okay, damp simple harmonic motion. Think of harmonic motion of the oscillating beam. Okay, it damps down until it finally comes to rest. Instead of quantum noise, we have a little bit of friction. It brings it to rest and damps out all the energy. Okay, and that statement doesn't hold up real well, but you get the idea. If you add R to an LC circuit, the same thing happens. You add a little bit of R in here, and it's still going to oscillate, but the oscillation will get damped out because you know that a current running through resistance is going to dissipate energy, just like friction will dissipate energy in an oscillating beam or an oscillating mass on a spring or a pendulum. Okay. Now, with that perspective, you look look at this equation again, and we see that the critical thing is how big is R? So when we get down to here, which we already have, we ask, okay, what's R? What's going to happen to R? Put everything on the other side with R, and you get R squared less than 4L over C. Okay? That's the limiting value at which this thing goes from positive to negative. This discriminant goes from positive to negative or negative to positive. If R squared is less than 4L over C, that means this term is small and this term is going to dominate and this term is negative. Okay. If R squared is greater than 4L over C, well, that's big enough to make this positive and give you an overdamped system. And I guess with jotting this down. Okay. This is down. This is undamped. In this case, you have an LC circuit with zero resistance in your inductor or capacitor. Looks like your inductor. It's going to have to be superconducting to accomplish. That can be done. Not this lab. Be done. Okay. So this is damped. Now, critically damped is the first one that doesn't oscillate. If you release a pendulum in molasses, it'll slowly come down to its equilibrium position, but it'll be so slow when it gets there, it won't have the momentum. Go past the equilibrium position. And you get just an exponential decrease. And that's basically very similar to the thing you have when you have the RL circuit. Okay. And actually, when I say it never actually reaches equilibrium, because your exponential function never actually reaches the asymptote. Okay. We have an exponential approach to equilibrium, and that's for either circuit. That would be like what happens with an RL circuit, because it does become an RL circuit. If the thing is critically damped, that means the discriminant is zero. R is negative R over 2L. And you have e to the negative R over 2L times T, which is very similar to what you have here. Now I'm worried about that too, but I'm not going to worry about it right now. Okay. And then in the overdamped situation, you get actually the sum of two exponential functions, and it comes down and approaches approach one. Okay. Anyhow, don't trust that comment, but it's pretty obvious. Now, let's go back to this. Now, there it is. Now, the form I was trying to put it in, I had the right instinct wrong. I wanted to factor this thing out, and I erased it. And here it is back. We could put it in this form. This now being imaginary, we multiply this back by the R over 2L, and we get this. Okay. So now our solution is solution can be written. Our characteristic value, our solution of characteristic equation would be this. plus or minus. Okay. This is negative. We take the square root of the negative of this, and that's going to be the square root of 1 over LC minus R squared over 4L squared times I. So now our solution is Q of P equals some constant. So I'll just call it A. We often use C for constant. You've got capacitance. We don't want to confuse things. So it's E to the negative R over 2L plus or minus the square root of 1 over LC minus R squared over 4L squared. Put my I right here. And this is A, E, the negative R over 2L T multiplied by E to the plus or minus I times the square root of this. Not writing very well. I'm also blocking the board. Okay. This implies you for some constant A E to the negative R over 2L times cosine of omega T plus pi for omega equals this square root of 1 over LC minus R squared over 4L squared. Now this is totally analogous to the solution you get for the spring mass dash pop, which I believe you dealt with in differential equations. Okay. This applies in this case. And I never was real specific about that. I didn't write it down here. I write it. It's hard to read, it's not well written. If R squared is less than 4L over C, here's what happens. In other cases, this is real, and it's some kind of a decreasing exponential or exponential-like function. Okay. Then again, try to observe a lot of this in lab Friday. Now, differential equations is not required of you. How you see you bypass this, you just memorize if R squared is less than 4L over C, or just memorize this expression here. I find it easier to derive than memorize, but given that my algebra skills get a little bit careless, I don't know if that's any longer true. But my memory's faded too. Anyhow, there's a process, there's a situation. And on a test this late date, given everything, I would probably write down this expression for you somewhere on the test. Without telling you what it means, you hopefully at least know what it means, so you don't actually have to memorize it.